He's a champion bridge player. He's had, in addition to this computer work, he's made his own crossword puzzles and had them published in the New York Times. And he even was able to sneak in Euler's equation of e to the pi I into a crossword puzzle. That's quite an accomplishment. He built and flies his own plane. And he once started an interesting discussion on a mailing list on what would you do if you had a constructive proof that P equals NP to get it out into the world before you could be murdered by the CIA. And I think he only started that so that if he crashes his plane, we'll think, So take it away, Matt.
Thank you. So yes, I did get Euler's equation into a crossword. Much more fun was making a crossword with Dana Delaney, which is a story in itself that I won't trouble you with. So a couple of things I'm going to assume in this talk. I'm going to stay over here. I'm going to assume that all of you know what crosswords are and how they work. This is the final of the American Crossword Puzzle Tournament. It's about 600 of the best solvers who get together once a year. They try and solve puzzles as quickly and accurately as possible. At the end of it, the 3 who have done the best get to solve the final puzzle on stage in front of the other 697, while Neil Conan and someone more obscure but with a better sense of humor make comments about what they're doing right and wrong. And they have headphones on so they can't hear any of the comments, and they're just struggling away up there. This is Dan Fair. He's won this tournament the last 2 years, and he solves about 7,000 crosswords a year for practice. So that's training for him. And this is Dr. Fill, looking thrilled at what I have done with his name. So there's sort of an obvious comparison. The other thing I'm going to assume is that everybody knows what Watson is. And there's an obvious comparison between Watson and Dr. Fill because at some level they're trying to do the same thing, right? They're trying to play games that require some level of natural language understanding and some amount of knowledge about the world. So let me tell you how the programs, first of all, how they differ, and then a little bit about how they're the same. So for example, Watson is named after Thomas J. Watson, the founder of IBM. Dr. Fill is named after a self-help guru. So that's one difference. We can also look at differences in terms of the resources available to these two projects. So for example, there are 25 people who work on Watson. There is one person, you're looking at him, who works on Dr. Fill. And to make matters worse, I actually have a day job. So I run on-time systems as what I'm supposed to be doing. And then about 10 minutes at a time when nobody's bothering me, I get to work on crossword puzzle solving. For the folks working on Watson, Watson is their job. So you've got 25 full-time people and one part-time person. That's the human resources. On the computational side, Watson runs in a room. So if you've seen any of the press coverage, you know that they've got this huge bank of computers and it fills up a whole room. Dr. Fill runs on a notebook. It runs on this notebook. I have turned off its internet connection. So there's a demo at the end where you'll see Dr. Fill doing its thing, for better or worse. And it's just going to be running on this machine. Watson has 16 terabytes of main memory. It's got about 3,000 cores. Well, I get to run on a notebook. Lucky me. I use about 4 gig of memory. The machine actually has 8. I use about 4, and I get to use 4 cores. So these are the computational resources. We can also talk about differences in the problems being solved. So in Jeopardy, for example, if you don't know the answer, you don't have to do anything. You just stand there and somebody else answers the question or not. It's all good. In crosswords, that doesn't count, right? If you take a crossword and you leave out a few of the squares, well, that's just wrong. It's not like you passed. It's wrong. You have to fill in every square if you want to get credit. In Jeopardy, button pushing is enormous. And so if you watch Jeopardy, you'll see the people, and they're all like pushing their buttons frantically. They've pushed a little bit too early, and then you get locked out for some number of seconds, and they're trying desperately to get back in. Watson is unbelievably good at this. And talking to Ken Jennings, for example, he believes the reason that Watson beat him has nothing to do with Jeopardy skill. It's because Watson, you can actually say, when Alex Trebek stops talking, wait 1/100 of a second and push the button. And it will do exactly that. It will never push before he stops talking. It will never wait more than 1/100 of a second. No human can keep up. Sometimes a human will get lucky and beat it. But by and large, button pushing gives Watson an enormous advantage in this domain. there is no button pushing in crossword. So there's nothing I can do that lets Dr. Fill have some sort of similar advantage. Another difference, and this is something that hasn't been publicized, is the Watson team actually negotiated with the Jeopardy folks, and certain questions were excluded. So there were questions that they felt would be unfair to Watson, and those were not included in the Jeopardy competition. The guy who runs the crossword tournament is Will Shorts. He's the crossword editor for the New York Times. You cannot negotiate with him. Okay, if I were to go to him and say, Will, this year Dr. Phil is going to be in the tournament, so please could you not have any of these kinds of puzzles? He would say, thank you very much, and he would put one in just because he can. So absolutely no negotiating. Another difference.
What kind of questions did they negotiate?
I don't know. I know that anything that was visual in any way was excluded. I don't know how far it went. Jeopardy questions are fair. You actually have to know this really obscure stuff, like who was president when Prohibition was repealed. But if you know who was president when Prohibition was repealed, you're good. You put it in the form of a question, you raise your hand, you give the answer, you get credit. Crossword constructors cheat. And I know this because I am one. So I've had about 30 puzzles in the Times. I'm one of the worst here in terms of the glee with which I break the crossword rules. But everybody who makes crosswords and the people who solve them like them to be unusual in some way. And let me give you a couple of examples. So here's a Times puzzle. I'm not going to go over there because it'll yell at me. The clue is Apollo 11 and 12, 180 degrees. And the answer is Snoisnunu. Okay? This is right. The reason this is right is because if you rotate it 180 degrees, you get moon missions. Now, how is a computer supposed to figure this out, right? It doesn't know that it doesn't even know you fill the letters in capitals. It doesn't know that an upside down W is an M. And N's stay the same. And so it has no way of figuring this out. So this makes solving puzzles like this by machine an enormous challenge. Here's another example. This is a puzzle of mine. The clue is they might be spiked, and the G has been replaced with an asterisk. And the answer is Enos. Now, Enos is the 78th most commonly used answer in crosswords. It's not because it's really a good word. It's because it's a short word and it has 4 really common letters in a good consonant-vowel pattern. Enos is, for example, the grandson of Eve. Enos Slaughter was a guy who played baseball an unbelievably long time ago, and he's in the Hall of Fame. So you can clue Enos this way, and it shows up. But what does Enos have to do with they might be spiked? Well, the answer is, I took the G out of the clue. So you got to take the G out of the answer. The answer is actually eggnogs. But if you take all the G's out of eggnogs, you get Enos. And in this puzzle, every single clue is like this. Now, this is not because this is like a normal thing in puzzles, right? This is the first time anybody did this. But having done this, every clue is like this. And in this case, there's actually no way that I'm aware of. Dr. Phil does terribly on this puzzle. It has no idea what's going on. But this is the kind of nonsense that crossword constructors put in front of solvers all the time. And that's their job, and the solvers like it. So back to our little table. To play Jeopardy well, you have to have some measure of intelligence in this bizarre sense that you're good at trivial pursuits. To do crosswords well, you have to be intelligent that way, and you also have to be clever, in that you somehow can duplicate these wrinkles that constructors put in front of you. So these are the differences. The big similarity is neither one of these programs, you'll see about Dr. Phil, neither one of them has any idea, no idea at all, about what they're actually doing. So let me play a little clip here. This is from the Jeopardy match.
Yeah. Let's go to alternates for 1,000, Alex. A thief or the bent part of an arm. Ken, what's our...
Okay, so the question was, or the answer was, a thief or the bent part of an arm. This is like a crossword staple. You really should be able to figure this out. And Watson says that's probably a knee. A thief or the bent part of an arm is probably a knee. 40%, which is why it didn't buzz in, less than the 50% cutoff. If it's not knee, it's probably waist. Well, that's a little better because you can bend at the waist. And then maybe it's crook. So the right answer is up here, good for Watson, but it really has no idea what's going on. It's just done some statistical pattern matching. This is what it came up with, and that's the best it can do. Here's Let me let this clip run a little longer.
Correct. What's that in the decade for 1,000? The first modern crossword puzzle is published, and Oreo cookies are introduced. Ken.
What are the 20s?
No. Watson.
What is 1920s?
No. Ken said that.
Okay. It really has no idea what it is doing. And Dr.Fill isn't any better. But neither of these programs has a clue as what's actually going on.
So, but was that because it didn't know that 20s and 1920s are the same, or because it wasn't that?
In that particular case, it didn't hear it wasn't listening.
Yeah.
Okay, so how Dr.Fill works, high level, and then I'll fill it in. It does a lot like what we do. It looks at the clues, tries to figure them out. Then it tries to fill in the grid. And as it fills the grid, it tries not to do anything wrong. This is not rocket science. This is how you fill crossword puzzles. When it analyzes the clues, I've got four cores. Each one is hyper-threaded, so I actually can analyze 8 clues at a time. When you see the demo, it'll look like this, where the clues currently being analyzed are colored pink. And it'll sort of race through the puzzle looking at all the clues. Having done that, all it's trying to do is it's trying to figure out for every fill, for every possible fill fj, and every clue ci, what is the probability that fj is right given the clue. So it's just trying to pre-compute all of these probabilities, and then armed with those probabilities, it's going to try and actually do the search. The goal in the search is you want to maximize the probability you solve the puzzle correctly, so you want to maximize the product of the probabilities that each individual fill is right. Equivalently, you want to minimize the negated sum of the logarithm that each probability is right. Each of these is between 0 and 1, so the logs are all negative, so if I take, etc. It's a little bit easier technically to work with minimizing a sum than maximizing a product, so I'm going to look at things that way. And as you do this, you have to honor all the constraints. So 1 down and 1 across typically share their first letter, so if 1 across is dog, then 1 down can't be cat, because the D from dog has to sit there. This is what's called a constraint satisfaction problem. If you haven't heard about constraint satisfaction problems, you actually have. Everybody knows all about them. The most common example is I give you a map of the United States, and I tell you color it in, and I'm going to give you 3 colors. That turns out to be enough for the map of the United States. Constraint satisfaction problem has a bunch of variables, and you're assigning values. The variables are the states, the values are the colors. And then you have rules. You have some sort of constraints, and typically when you're coloring in a map, the rule is that states that share a border have to be different colors. Because if you color them the same color, then you wouldn't know that Wyoming and Colorado, for example, are 2 different states. In general, people solve these with some kind of backtracking algorithm. You start coloring and you color for a while, and then you get stuck and you back up and color something different, and you get stuck and you go forward and backward until you actually find a solution. One wrinkle that turns out to matter in this domain is people talk about what are called weighted constraint satisfaction problems. So let's say I give you this CSP, I tell you color the US using red, green, and blue, but the inks cost different amounts. And the goal now is not only to find a solution, but to find a solution that minimizes the cost of the ink. So if blue is the cheapest, you want to use blue sort of for Texas because they always make Alaska look smaller than it is. So this is what's called a weighted constraint satisfaction problem, and that's what a crossword is. So it looks exactly the same. The variables are the word slots, the places at which you have to assign values. The values are the things you might fill in there. So snowy, snoo, whatever, or the more normal words that show up elsewhere. The constraints say that the crossing letters have to match. So at 38 down here, the second letter is an S. I've got to put a word there that has S as its second letter. And the weights are the logs of the probabilities that I talked about before. So the goal is to minimize the total cost of the sum of the negation of all of these logarithms. Now, I don't really care if these are logarithms. I just care if there's a cost associated with each word in each slot. So I'm just going to call that the cost of putting fill J in response to clue I. Is everybody good? Okay. Having written it this way, it's a weighted CSP. This is, at least on the face of it, good because there's a huge academic literature on how to solve weighted CSPs. So all I have to do is I've got to go and take all their good ideas and apply them to this domain. So before I tell you how I do the search, a tiny bit more about the cost function. I use really simple statistical stuff. I periodically get brave and I try and use fancy natural language processing or something sophisticated, and the performance of the program always degrades. So I use really simple statistical techniques. I do have a huge database of pretty much every crossword clue since 1990. I use that. And Google was kind enough to let me run all of the words in my dictionary through Google to see how many hits it got, and I use that to bias the results as well. I was trying to solve the same problem Watson is. I get a common sense, the bent part of an arm, and I'm supposed to say crook. I can tell you up front, I am not nearly as good at this as Watson is. So I'm running on a notebook. I don't have nearly the resources. I haven't done nearly the natural language work they have. My goal is not to, in Jeopardy, you got to get the answer right. In terms of Dr.Fill, because of the search constraints provided by the constraint satisfaction problem, if I can get the right answer in the top 100 fills, I'm probably good. So that's sort of my goal. And it turns out that the problem is not getting the right answer in the top 100 fills. The problem is stuff like snow, which is not in the dictionary. It's in the crossword, it's not in the dictionary. Or you might have a crossword that was all about rabbits, right? So that means that the crossword constructor took all these normal phrases and somehow torqued them around so they had to do with rabbits. So instead of Bonnie and Clyde, you have Bunny and Clyde, which is supposed to be in the crossword. You might have hair today, gone tomorrow. Who knows how they clued that? And they just do this all over the place. None of these are in the dictionary, but you've got to put them in the fill. Okay, I've told you how I analyze the clues. Let me move on to filling the grid, which is the interesting part from a research perspective because it's an interesting CSP. To tell you how to solve a CSP, I've got to do three things. I've got to tell you how I picked the variables. So at any given point in time, you've got to decide what word you're going to fill in. Having decided I'm going to work on 36 across, I've got to tell you, okay, what are you actually going to put into 36 across? And lastly, presumably it's going to make some mistakes somewhere along the way, and I've got to tell you how to search around the space of possible fills to try and find a better answer than you currently have. Bottom line, the goal is not to make mistakes, and the way I wind up interpreting that is you fill in the word that you're the most confident with the answer that's the least dumb. So that's how Dr.Fill works. And I'll give you lots of details about how it actually makes these decisions. So let me start with variable selection. As I told you, lots of research on this. So there's conventional wisdom on what you do, and the bottom line is take the most constrained variable and fill that in next. So if you go back to map coloring, imagine that you've colored a couple of states, and the only color left for California is blue. You should probably color California in now blue before you screw it up. So, maybe Nevada isn't colored. If you color Nevada blue, well, now there's nothing left for California and you're stuck. So take something that's maximally constrained and value that next. So one thing, as I said, take the variable with the smallest live set. And by the live set of a variable, I mean the things that are still possible. So the colors for a state, because no neighbors have that color. In a crossword, if you've got a 6-letter word, A blank E blank blank blank, the live set is words. You ask your friend, can you think of a 6-letter word for Munchkin, A blank E blank blank blank? So that's the live set. Another possibility is to pick the variable that has the highest minimum cost. Your goal is to minimize the cost here. So the variable that you might want to do next is the one that has the highest minimum cost because you're already in trouble. And before you get in more trouble, fill that one in. So I took both of these, I tried them both, and they were hopeless. Absolutely no success. The reason, roughly speaking, is that both of these, in a crossword, are really an indication that you are probably dealing with out-of-the-language fill. So you've put in a couple of letters in this long answer, and there are only two possibilities left. Well, maybe what you're supposed to put in isn't in the dictionary at all. And if you start filling these in as soon as they become constrained, you have all this stuff that's out of a dictionary, you're getting it totally wrong, and you just wind up filling the puzzle terribly. So this is too hard for me, this variable selection problem. So let me look at value selection instead. Standard wisdom, not rocket science, you've got a cost function, put in the value that has the least cost. You're trying to minimize cost, so, well, minimize cost. That didn't work. The reason it didn't work is because my cost function sort of stinks. Yeah, the answer is probably in the top 100, but that doesn't mean it's the top answer. And if I just put in the top answer, I probably get it wrong. So the cost function just isn't good enough, isn't accurate enough to support that heuristic in terms of variable choice. But what I can do is I can use a little bit of look ahead. So let's imagine at any given point I'm looking at clue I, and I'm trying to fill it in, and there's some live set Li for that clue. I can look at all the fills that are in the live set and consider the minimum cost of that fill. That's sort of the minimum cost that I will eventually have for filling in clue I, and I'm going to call that the cost of clue I. And now, instead of using the fill that minimizes the cost of that fill for that clue, I'm going to use the fill that simultaneously minimizes that cost and the cost of all the crossing words. Because when I put a word in, I've actually messed up all the crossing words. I've restricted their live set. And if I restrict their live set in some horrible way, then I know I'm going to incur a very large cost when it comes to putting in the crossing word. So one way to think of this is every time you put a word in the puzzle, you sort of damage the fill. It just got worse. You incurred some amount of cost. And what I'm going to do is I'm going to put in the fill that minimally damages the puzzle, given not just this word, but the crossing words as well. I'm doing a little bit of look ahead to find a better answer. And this turns out to be pretty good because the fill that C by itself doesn't distinguish, the crossing words help you with. So armed with this, let me go back to the variable selection question. So I've got this value. The value of fill F in slot I is the cost of putting F in slot I plus the corresponding cost of all the crossing words. And now I can define the value of filling slot I at all to be the minimum of all those fill-based values. So this is the minimum damage I can do to the puzzle if I fill in slot I. And now it's pretty obvious what you should do, namely choose the variable that minimizes V of I, because that way you're doing the minimum damage overall each time you insert a word. Well, this is obvious, but it doesn't work. The reason it doesn't work, and I implemented this, so actually you're following me as I implement things and trying to make Dr.Fill work, except you're going much faster. The reason this didn't work is because the software ended up putting in all this non-committal junk. So it would have some three-letter word over here, and it would put in R, because A is a common letter, so it doesn't really mess up the crossing words, and R is a common letter, so it doesn't mess up the crossing words, and E is a common letter. That's great. And then it would put Eon over here, and then it would put Enos over here. None of these had anything to do with the puzzle, but there were these wonderful common words with lots of common letters, and it would just scatter them all over the puzzle, and then it would realize it was totally stuck. So rather than do this, I've got this V, which is the minimum damage you can do by filling in word I. And let me introduce min 2. That is the damage done by the second best choice. So this is the best word, this is the second best word, and the difference between these two really tells you how confident you are that the best word really is right, because it's really getting separation from the next best word. This is always negative because the damage here is smaller than the damage here. So what you actually want to do is you want to fill in the word for which this value is as negative as it possibly can be, because that's the word in which you really are the most confident. So that's what Dr.Fill does. It's the variable for which you have the most confidence in your value selection. So pick the value that does the least damage given one ply of look ahead. Pick the variable for which that value is the one in which you're the most confident. And if you do this, you actually get a solver that looks like it sort of knows what it's doing. In retrospect, I should have started with this, but I wasn't smart enough. Okay, you do this, you're still going to make mistakes. The problem is basically NP complete, so you're still going to make mistakes one way or another. You still need some way to navigate the search space. One of the things about crossword puzzles, they generally, not always, but they generally have a unique solution. So there really is, hopefully, a best answer that you're looking for, and you have to use search to find it. The difficulty is that if you make a mistake near the root of the tree, you're dead. Because all of these normal chronological backtracking schemes have the property that once you expand a node, you're sort of stuck there.
you don't actually need really good connection between the clues and the values, because you know that if you start putting in random clues,
If you Yes, but you don't realize it as quickly as you would like. I can come back to that at the end. It's more subtle than that, but there is certainly information there. You can't search the whole space of possible fills. I mean, there are about 75 words in a crossword. There may be 10,000 dictionary words of each length, so the raw search space is 10,000 of a 75th. It's completely impractical to look at it in anything like its entirety. As far as I know, the best way to solve a problem like this is to use something called limited discrepancy search, which I did with a student of mine named Will Harvey. So let me tell you how that looks, and then we can look at it in the setting of crossword puzzles. So here's a simple binary tree. And if you do normal chronological backtracking, you wind up just searching the tree from left to right. Each time you decide to backtrack, you go back as little as possible, and then you go forward again. And the problem is, if you make a mistake at the root, so this top thing is wrong, the whole left side of a tree is wrong. But you're not going to get to the right side of the tree unless you look at the left side of the tree in its entirety, and you don't have time to do that. So what Harvey noticed, he said, well, instead of looking at the nodes just as they sit, start counting the discrepancies. And by a discrepancy, I'm going to assume that the left choice here is always the heuristic choice. So the heuristic is always telling you to go to the left. A discrepancy is any time you don't do what the heuristic says. So there's one node here that has no discrepancies because you go to the left every time. There are 4 nodes that have one discrepancy because you have to pick the level at which you choose to go to the right. There are 6 nodes that have 2 discrepancies. Then there are 4 nodes again that have 3 discrepancies, and there's one node all the way on the right side that has 4 discrepancies. And the basic plan is that what you're going to do, instead of evaluating the tree from left to right, you're actually going to evaluate the tree in discrepancy order. So the first thing you're going to do is you're going to look at the 0 discrepancy node over here. If that's no good, or if you don't like it, or if you just want to keep looking, you're going to next look at the 4 1 discrepancy nodes. And the way I'm going to structure the search is I'm at the root node. I'm allowed 1 discrepancy. I'm going to use it as early as I can. So the first thing I'm going to do is I'm going to go right. And now I don't have any discrepancies left, so I've got to go left, 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 and I evaluate this node second. Next, I go left at the root, but then I go right as soon as I can, and I evaluate this node. So I'm going to evaluate the 1 discrepancy nodes from right to left because of that choice. I'm going to evaluate the 6 2 discrepancy nodes from right to left, then the 3 discrepancy nodes, and at the end I'm going to evaluate the last node here. And the whole point of limited discrepancy search is that this node, instead of being evaluated 9th in the tree, is now evaluated 2nd. And LDS is incredibly effective at jumping from one part of the tree to another. So that's the deal. It's an iterative algorithm. Iteration n says look at all the nodes that have discrepancy less than n. It's iterative, so you're going to repeat some work. So iteration 5 is going to look at all the iteration 4 nodes again. But if you think about it, on a tree of depth d, iteration n is about d times as big as iteration n minus 1. So if the crossword tree is of depth 75, iteration 4 is 75 times as big as iteration 3, so it doesn't matter. All the work is in the last iteration. You avoid this problem where if you make an early mistake, you're dead, because you're very effective at jumping from one part of the tree to another. The only issue, so in the binary tree I showed you, it's really obvious what a discrepancy is. A discrepancy is don't follow the heuristic. But in a non-binary tree, it's much more subtle. So here's a little piece of a crossword tree. I'm looking at 4 across, and I can put in dog, cat, man, or elf. Who knows why? And probably zillions more choices. If I put in dog, I next look at 3 down. 3 down uses the O in dog as the second letter, so it can be food, John, or golf. And now I want to somehow do a discrepancy here. I don't want to put dog in for 4 across. Well, what's a discrepancy? The obvious answer is a discrepancy is make any choice other than dog. Well, unfortunately, that doesn't work. The reason it doesn't work is because there are a lot of choices other than dog. So LDS 1, instead of having 1 successor here, has 1,000. And if you're allowed 2 iterations, you have 1,000 squared. So the search gets completely out of control very quickly. All right, so that doesn't work. What if you said, okay, cat is 1 discrepancy, man is 2 discrepancies, elf is 3 discrepancies, so you just associate a discrepancy each time you move to the right. Well, that turned out not to work either. The reason that doesn't work, you picked 4 across because you were confident that dog was the right answer. But if dog is the wrong answer and you eliminate it, you have no reason to believe you really have a strong preference between cat, man, and elf. They could be, I mean, they're in the right order, but they could be incredibly close. So now you're basically back to putting something random in. Okay? To fix that, you could branch on a different variable. So you could say, no, don't branch on 4 across. That's my discrepancy. Branch on whatever. Well, that doesn't work. The reason that didn't work is I said, don't branch on 4 across. So the machine said, okay, here's 4 across. I'll put Harry down here. Oh, good. Now I'm going to branch on 4 across and put in dog. Because whatever made dog attractive before still makes dog attractive. So it would do something unrelated elsewhere in the puzzle and then go back to putting in exactly the thing that you wanted LDS to avoid. So that didn't work. What did work is to exclude the value of dog for 4 across. And this actually worked. So what I do is I say, okay, no putting dog in at 4 across. Do you still want to branch on 4 across? If cat, man, and elf are close, the machine won't branch on 4 across. It'll branch somewhere else. If cat, man, and elf are not close, it'll stick cat in. But whatever it does, when it eventually expands 4 across, and it has to, when it eventually expands 4 across, it's not allowed to put dog in. And that's what I think of as a discrepancy, and that actually works. So, pick the variable, the value that does the least damage, pick the variable in which you're the most confident, and to manage the search, use limited discrepancy search. We're disallowing a specific value for a specific variable is what you think of as a discrepancy. This is basically what Dr.Fill does. There's one other technical note I want to make. And that is I did this, I ran it, it was pretty good. And what I noticed was would often finish a puzzle and there would be a single letter that was wrong. Now, a lot of times letters are wrong because it just thinks its fill is better because the statistical stuff isn't working or isn't working well enough. But a lot of the times it actually knew that letter was wrong. So it would have bag, and the right answer was bug, and it would actually know that if it could change bag to bug, the quality of the solution would improve. But when it filled in bag looked like it was really the best word, so it stuck it in, just got it wrong. What that suggests is that the program would benefit from some kind of post-processing. So when you're done, you have a solution, and just try dinking with it. The simplest thing you could do is take every letter and try every possible replacement and just see if it makes it better. If it makes it better, good. If not, fine. The problem is there's another technique that's used universally in solving weighted CSPs. It's called branch and bound. And that looks like this. So presumably at most of the time you've already done LDS 0. You've got a solution in hand. Say that solution is cost 86. And now you're expanding the tree, and you're somewhere in the middle, and you've already incurred cost 88. You can stop, because everything you do damages the quality of the solution. So in a situation like this, you can prune everything under the current node. It's not going to be better than the 86 you have in hand. This is used absolutely universally in weighted CSPs. Just generally assume if you don't do this, your search is pathetic. The problem is that post-processing and branch and bound are inconsistent. You have to actually do one. You have to commit to one or commit to the other. The reason is that branch and bound, the basic notion, is that you can look at a node that's internal to the tree and draw some useful conclusion about it. Namely, it's already too high. The cost is already too high. Post-processing, the basic notion is that you can only really evaluate a node at the fringe of the tree. Because until you get to the fringe, until you do the post-process, you might have a node that's going to post-process really well and you just don't know it. So the question is, do you want to post-process? Do you want to use branch and bound? At some level, this is an experimental question. So I implemented both. And it turns out that post-processing is way better. In this domain, post-processing is massively more effective than branch and bound. And one of the cool things is you can actually understand why. So remember the basic heuristic. Pick the value that does the least damage. Pick the variable that you're the surest of. What this is doing, you're always trying not to incur any cost. So you wind up pushing all the cost down the tree. Now you do incur cost. Eventually, at the very fringe of the tree, you all of a sudden incur a bunch of cost. But in the middle of the tree, you don't incur any cost. And what that means is that branch and bound winds up only being able to prune nodes right near the fringe because it just doesn't incur enough cost until it's way down near the fringe. That means it has almost no computational value because pruning a node right down near the fringe of the tree when you only got 2 words left to fill in, that doesn't save you anything. You're just going to fill those 2 words, you're going to be done. You want to prune nodes, you want to use branch and bound to prune nodes way up here. So branch and bound doesn't do much. And I actually, when I realized this, I took branch and bound out. I didn't put post-processing in. I just took branch and bound out, and the performance didn't get worse. That's how little value it had. But post-processing, this argument has nothing to do with post-processing. Post-processing really does add value. So given the choice of a technique that doesn't add value in this domain and one that does, it's not surprising that the one that actually helps does better. So that's Dr.Fill. The value it does the least damage, the variable you're the most confident in, LDS as I've described it, and lastly, use post-processing instead of branch and bound to control the residual search. So I'm going to give you a demo in just a second. Before I do that, there's one sort of high-level point I want to make. If you look at all the work on game-playing programs, so starting with chess, Garry Kasparov, when he plays chess, he looks at about 20 successor positions to the position he's currently in. Now, he's Garry Kasparov. They're the right 20 successor positions. Deep Blue, zillions is a technical term. It means 10 to the 10th. Deep Blue looks at a ton of positions. It has no idea what it's doing. But the sheer power is what gives it its strength. There's been a lot of work on computer poker. So people play poker. We use all these rules. We have table presence. And they tried to make programs play poker like this. They were terrible. So they eventually realized that they could take poker, reduce it to systems of millions of linear equations, get this huge linear optimization problem, solve it to get a strategy. If this is the situation you're in, bluff 6.8% of the time and fold the rest. Then they just run the strategy. And this works. This produces poker players that are as good as people, basically, in Texas Hold'em. I did a lot of work on bridge in the late 90s. People play bridge using pattern recognition. You look at a hand and you say, oh, I need an end play, I need a finesse, I need a squeeze, whatever. Again, people tried to make bridge programs that worked this way. They were hopeless. And I came along and I said, no, just search the whole thing. It's not that big a space. You've got the resources, just expand the whole tree, do what rates to be best, and you're good. And all of a sudden, computer bridge players, instead of being terrible, were good. Jeopardy. People solve Jeopardy with all of this knowledge that they've crammed into their heads. A Jeopardy champion can answer about 92% of the questions correctly. Someone who loses on the TV show can answer about 90% of the questions correctly. This is not what Watson does. Watson just uses statistical pattern matching. It takes the query, does a little bit of analysis, looks through a huge amount of data, and figures out what appears to be the right answer. Crosswords, same thing. People use this aggregated knowledge, just as obscure as Jeopardy. They use imagination to do things like this moon mission thing, and they're 100% accurate. Everybody who was on the stage in the slide at the beginning had solved every puzzle leading up to that point completely correctly. Dr.Fill, not like that. Statistical pattern matching, straight numerical techniques, lots of number crunching, and then lots of search using the crossing word. No idea what it's doing. It's just trying to make up for that with pure computational horsepower. On the human side, pretty much everything is pattern recognition. On the computer side, everything is search. And I just want to argue, and then I'll get to the demo, this probably means something. It means that the natural domains of competence for people and machines are going to be different. There are things that we do that machines are going to be lousy at for a long time. There are things that we do that they're going to be better at, and they already are. One of the nice things about games is they actually appear to be sort of in the middle, where right at the moment, our performance using pattern recognition and machine performance using search is sort of comparable. So, okay. let me do the demo. What I'm going to do here, and I do not like giving this talk on Fridays, so I'm going to show you Dr. Phil solving today's puzzle in the New York Times. I have not seen this before. It could be I could look great. I could look like a total goat. The reason I don't like giving the talk on Fridays is because the New York Times puzzles get harder as the week goes on. So Monday is my day of choice for giving this talk. Thursdays and Sundays are about the same, but Sundays are bigger. Thursdays are where all the weird stuff comes in. So the moon missions thing was a Thursday. Friday and Saturday are probably harder than the Crossword Puzzle Tournament puzzles because you have to solve the tournament puzzles so quickly. They don't have really weird stuff, for which I am eternally grateful, but they do have very obscure words and very obscure fill. So let me start this. Okay, so here it's analyzing the clues. When it starts to fill, the GUI knows what the right answer is. So if a square comes out yellow, that'll mean it's wrong. The program obviously doesn't know, but the GUI knows. Okay, so this letter is wrong. A couple are wrong up there. And now it's gonna do the post-processing, and then it's eventually going to start with the limited discrepancy stuff. So the post-processing fixed the error down here. The letters that are colored red, that's the word that is currently being eliminated in LDS. So right now it's looking, well, what if I don't allow or to right there? Well, it actually came up with something worse, namely or so, but it's gradually fixing more and more of what's going on. And like I said, I have no idea if it's going to finish having sorted this out or not, because I haven't seen this puzzle before. I can look at individual things. Let me tell you what the colors mean. So as we get later in the week, you don't see much green. Green means I have seen this clue before. So errata, printed slips, 6 letters. Errata is the right answer, and this clue somewhere, sometime has been used for errata before. Blue, each letter is colored sort of the worst of the 2 letters for the crossing words. So this means it's actually seen, that green means it's seen both of those before. Blue means I haven't seen this clue before, but I've seen something like it. So one down is steel work, and that's an essay. Steel is apparently some essayist. I'm terrible at crosswords. I don't know any of this stuff. So is an essay. And that it hasn't been clued before, but probably steel was clued in some other clue that used steel to eventually get to essay or maybe work. So it eventually decided that essay was pretty good. This means it's done. It thinks it's not going to improve this. Black means I don't know what this has to do with the clue, but at least it's in my dictionary. So this has been, so the fact that my screen shrunk has made this. This is actually singing telegram. And the last letter has been pruned off because of the shrunk screen. I'm sorry. Singing telegram is in the database. It's called special. It's clued as special delivery of a sort. And probably singing telegram has not appeared a lot in Crosswords. It's 15 letters long, and it didn't come across. It wasn't clued anything like this. But at least it's in the database. That's good. Purple means I don't really know what's going on, but at least the fill is a collection of words like Bunny and Clyde. It would really not know what Bunny and Clyde meant, but it knows about Bunny, and is a word, and so is Clyde. So here you've got orgs, either org, score, or orgs, core, but org is a word, comes up all the time in crosswords. It's a, URL ending, and score is certainly a word. In reality, the right answer, which is perhaps no less obscure, is hog score. The clue is curling rink line 7 yards from the tee. Nobody in the United States curls, but if you curl, apparently there's this thing 7 yards from the tee that's called a hog score. Hog score is not in Dr. Phil's dictionary, so even it actually thinks its answer is better. Its answer is 18 something, and the right answer has a cost of 20. So that's the deal. So it's done. 4 letters wrong. Could be better, could be worse. And that's really all I have to tell you. So if you've got questions, I will happily answer them. Go ahead.
This is great stuff. Great stuff. This is really interesting.
Thank you.
I was thinking about this on the way down here, and I was thinking about the problem of filling in letters in a grid. And
So-
you've done all your work in your, I guess, 75 to the 10,000th space. And why not the 400 to the 26th space?
So both spaces are intractably large. Every constraint satisfaction problem has what's called a dual, where the roles of the variables and the values are sort of reversed. So you can do crossword puzzles a letter at a time, and then you obviously have matching letters because you put it in a letter at a time, and the constraint is now that EMMA has to actually be a word. So you have this huge explosion in the number of constraints, which makes the search hard. The real reason I don't think that works, there are two reasons I don't think it works very well. One is it makes it much harder to exploit the clues directly because you have this indirect thing. And probably more important, what really makes crosswords tough is the stuff that's not in the dictionary. And to do that, I don't have a dictionary that includes Bunny and Clyde, but I can get it if I look at it a word at a time. And in fact, what Dr.Fill does is as soon as you have, I think it's 4 or fewer letters, it actually looks at every insertion of letters into those 4 slots, sees which are multi-words, sequences of words, and tries to arrange the rest of the fill to allow those multi-words to happen. And doing that a letter at a time, I found more confusing. So that's why I structured the search this way. And it's, would a letter at a time do better? It might, but there's a lot of work. Pandu?
So this is really very cool. I missed how you handled out of vocabulary words. Is it just that they have very high cost?
So the cost goes up. So there are a variety of costing mechanisms. So for example, based on the clue, based on in the language, if it's in the language, how many Google hits did it get? Those are weighted relative to one another. There's a penalty for not being in the dictionary, but appearing, say, in Wikipedia. So MMYY appeared in a puzzle. That appears 3 times in Wikipedia. You all know what it means. It's August 2012. 08/12 format is MMDY. MMYY. Everybody knows what it means. It was not in a dictionary, never appeared before in a puzzle. It's got to get some penalty. So there's a penalty for not being in the dictionary but being in Wikipedia. There's a penalty for not even being in Wikipedia but being a sequence of words. And there's a nasty penalty for being nothing. Like moon missions upside down, that's nothing. In that puzzle, there were a bunch of those rotate things, and it got about half of them right just because the crossers were so good. It said, I know it's nothing, but it's the best I can come up with. And if there were any in this puzzle, they'd be in red. So cost is gradually accumulated. And it's really simple. It's basically just Bayes' rule. So cost gets accumulated from all these things. I know what fraction of the time in puzzles words are nothing. And then I do a bit of scaling that I tune to optimize performance. Is that an answer? Okay. Yeah.
So the last bit there with it making up words like ORG score and actually deciding that it thinks that's better filled than the actual solution is kind of interesting from an editorial standpoint. Do you think you could turn this into something where, given a crossword, you could actually edit it and make a better crossword using some different constraints, like words with Z's and J's are more interesting to the solver, say?
That's a great question, and the answer is no. And the real reason, it's just an awesome question, the real reason is that what makes crosswords interesting to a human is exactly the stuff that confuses the program and the program thinks are terrible. So as a solver, as a constructor, the stuff I try and put in is exactly what messes the program up. But great idea. Yeah.
So what would you what would you do differently if you didn't have the constraint of a laptop and you said, hey, I can use thousands and thousands of cores?
What I would do differently is I would go to the Watson people and say, give me your code and your machine, and I would use that to provide the cost function. I mean, it had a cost function, and I would use that to provide a much better cost function, and then I would expect that exactly this search algorithm would essentially get everything right. Yeah.
So are you still actively working on this? And if
I am.
Do you have like ideas for?
No,
what
I
you want
have.
in the future?
There's a bunch of stuff. It's all well. It's generally at this point down in the bits because the bits are where the problems are. Pandu is being incredibly gracious and helping me. So I built my dictionary based on Google hits 5 years ago, and the language has changed. For example, Octomom is now in the language, and it didn't used to be. So I've given Pandu a new word list, and he's running it for me, and I'm grateful for that. Another measure of how common something is if you look at Wikipedia titles, all the Wikipedia titles are in the dictionary. Wikipedia keeps statistics on how often each article is accessed. You can download them. It's a terabyte of data. It takes a little while. Well, it takes a little while for me. You guys probably take 12 seconds, but it takes a little while. And you can then aggregate it to get another measure of how common words are. I know that the dictionary that I have, which has about 3 million scored words based on how good they are in crosswords, has lots of problems. So Colin Powell, for example, came up and it's really low. And, the guy's pretty famous, so he probably should be higher. So fixing that dictionary will help because it will indirectly fix the heuristic. Just a bunch of stuff, a little bit better time management. Dr.Fill, the way the tournament works is when you're done with the puzzle, you raise your hand and then they collect your answer. And if you raise your hand at 13 minutes and 27 seconds, you get credit for 13 minutes. So Dr.Fill tries to run right down to the minute, but I can do that time management a little better. But all of this is sort of down in the bits. I think at a high level, this program really works. I mean, you saw it. The program works pretty well, and the search works. I mean, what's exciting to me is that the search actually works. So you saw it take a puzzle where it had probably a dozen mistakes and eventually get it down to just these 4.
So going back to the previous question about having, say, access to Watson's resources, it's not clear to me that would actually help you, because your search is running really fast, and so getting a better heuristic function does not seem to be your problem. And so I was wondering if you could go back and comment on the earlier question about having the unique solution and how much that helps you actually get to the answer.
Okay, let's see. There are a lot of questions there. First of all, in general, if you ask me a question again, I'm not going to change my answer. What I do when I analyze puzzles, so I let Dr.Fill solve a puzzle and I look at what it did wrong. And in this particular puzzle, it's made what I'm going to think of as one mistake because it's all right there. And you can't fix it without fixing the whole thing. Back when there were wrong letters here, that's 2 mistakes. And then what I do is I look at the mistakes and I break them down into search errors where it actually thinks the right answer is better. It just didn't find it in the search. And heuristic errors where it thinks its answer is better and it's just wrong. Right now, it makes about half of each. So there is work to be done on the search. I can't figure out anything better to do. And there's certainly work to be done on the heuristic side. If the heuristics get better, not only do I avoid some of the heuristic errors, but I suspect I will avoid some search errors because it will be pushed toward the right solution. So that's why I believe Watson or a better dictionary or anything that improves the heuristics will help me a lot. As far as the uniqueness of the solution, well, the first thing I want to say is the example where crosswords have non-unique solutions are just so cool. So the election day in '96, there was a puzzle that day that appeared in the New York Times, and it had 2 7-letter words across the middle. And the clue for, say, 32 and 33 across. It said 32 was with 33 across, tomorrow's headline. And 33 across was elected. And 32 across could be either Bob Dole or Clinton, depending upon what you did for the crossing word. So the B or C was a 3-letter word, something AT, and the clue was Halloween animal. And it could be bat or cat. And all of the clues were like this, and it had 2 solutions, and people actually didn't realize this, and they thought it had to be Clinton, and they called the Times just furious that the New York Times crossword puzzle had come down on one side of the election or another, but it hadn't. So that's just a story. As far as the value of the unique solution, I don't know how much it really helps. The fact that I do always want to climb until I find the best solution I'm ever going to find, but I've only got 15 minutes or 25 minutes or however long they give you with the crossword tournament. So what Dr.Fill does, this answers is that other question a little, is it actually spends, I believe, 35 seconds, and if nothing good has happened in the last 35 seconds, it then runs out the minute. So that's how it actually tries to manage its time. And I picked the 35 seconds, but I tried 30, 30, and 40, and 32, and on a batch of 100 puzzles, 35 is the one that worked the best, and eventually you're just chasing your tail. So that's what I picked. So I don't know how much specifically the unique solution helps it. Yeah.
I guess. So I understand there are programs available to help people construct crossword puzzles. What tools do they use? Is there any overlap between the tools they use and the tools you use?
So the tools that they use to construct, people use to construct crosswords, and I use one. I have written one that I sometimes use when the commercial one is no good. There are a couple of commercial ones. They're basically constraint satisfaction engines. You give them a dictionary. You can tell them what the scores are and tell them try and use high-scoring words, but they don't do it really optimally. They are not terribly sophisticated in terms of constraint satisfaction. They are definitely chronological backtrackers. They don't even chronological backtrackers. You can, when something goes wrong and you get stuck, you can learn the reason, and the programs don't. So what you'll do is you'll see them fill in a piece of the puzzle, and they'll end up with an S leading into a new open section that they then try and fill in, and it fails. So then they backtrack, and they erase all this stuff, and they fill it in again, and they put an S back there, and then they're it's going to fail. It's going to fail for the same reason. They don't know. So you just watch them thrashing. So they're not terribly sophisticated constraint engines, but they're invaluable. The GUI is good, and as a constructor, they're helpful. I don't use them to construct puzzles. I put in a word, and I say, okay, I want to put this word at 2 down, and then I run the filler. And if it fills the puzzle, I know I probably can put that word at 2 down. I've got to finish filling it. But if it says I can't, it just saved me a lot of time. I got to put something else at 2 down. So I'm still doing a lot of the construction by hand, but the tools are really helpful. Yep.
I guess the follow-up is, could you use this program to make a better crossword construction tool?
That was asked, and the answer is I don't think so, because
I understand that you can't do it to create an entire puzzle from scratch, but to
take
the existing tools and just make them better.
So I still don't think so. Roughly speaking, the existing tools. So if you ask me how would I make the existing tools better, the answer would be I would improve their constraint satisfaction engines. But their constraint satisfaction engines are sort of different than mine. They typically, as a constructor, one bad word can destroy a great puzzle. One good word cannot make a puzzle. So what that means is you're optimizing something very different because you're trying to maximize the minimum. And it's not aggregated so much. It's all just, can I fill this without using words of this quality or worse? It's a different technical problem. They still don't solve it well. But the specific techniques that I use here to solve this weighted CSP I don't think are terribly applicable on the construction side. You really just want to say, okay, can I fill from here without using anything horrible?